Welcome to the Journal Computing Information Science and Engineering JSAS Spotlight Talk of this month. Today, it is my pleasure to present to Professor Christian Soize. Professor Soize is one of the best known uncertain quantification researchers in the world, and he had been working on topics of uncertain quantifications, computational mechanics, stochastic dynamics. There are probably over 300 publications, including 9 books on uncertain quantification and stochastic dynamics. In the most recent years, Professor Soize is working on one of the most exciting topics on UQ, is called the probabilistic learning on manifold. It's a very smart way to integrate uncertain quantifications and the dimensional reduction, and as well as, of course, the generative machine learning. Today, and Professor Soize is going to give a talk on his most recent work on the probabilistic learning on manifold, published recently in JSAS, and the title of the paper is Updating Nonlinear Stochastic Dynamics of Uncertain Nozzle Model Using Probabilistic Learning with Partial Observability and Incomplete Dataset. With that, and Professor Soize, and please take over. And
okay, it's good.
Yes, we're good.
Thank you, Ian, for the presentation. So, what is the framework of this paper, this talk? I consider a high-dimensional nonlinear computational dynamics model of a nozzle. In the case of three-dimensional elasticity, for which we consider geometric nonlinearities. So the elasticity tensor of the material is uncertain and is considered as an uncontrolled random parameter. This mechanical system is excited by a stochastic random load, which is a random pressure field applied to the shell. And this stochastic excitation, stochastic process, is driven by random control parameters. This scheme summarizes the definition of the nonlinear stochastic computational model with random control and uncontrolled parameters. So this is a nonlinear stochastic equation, which is written here in nonlinear dynamics. F is a stochastic excitation depending on the random control parameter. And Y is a vector of the random displacement. And the stochastic equation depends on a random uncontrolled parameter U. I will explain later what is U and W. So there are 2 random observation operators. One, O, for defining the random observation for prediction, and another one, which is OID, which is the identification random observation, identification that will be performed with a target dataset, So from a probabilistic point of view, the prior probability model, the joint probability model, consists of given the probability for U, the uncontrolled parameter, the control parameter W, and the stochastic process, that is the excitation of the dynamical system. The objective is to construct a predictive statistical surrogate model for the updated conditional observation, or UD for updated, depending on W0, which is given, a given value of the control parameter of the observation O. The updating is done using a small target dataset, which is related to the identification observation OID. So what is the proposed methodology? This methodology uses probabilistic learning on manifolds, PLOM, introduced with my colleague Roger Ganem in 16. For the case of constraints by a target, for which basic development is given in this paper in 20. And using a formulation of the Fourier transform of probability measure recently published in 23. So the predictive statistical surrogate model from a small incomplete data set is based on statistical conditioning that is explored using the learned data set as explained in the paper in 24. So just a few words concerning the construction of the training dataset and the projection of the target dataset. So the training dataset is made up of ND point with ND small related to a random vector X in high dimension, which is a concatenation of O, the observation vector, OID, the identification observation vector, and W, the control parameter. So a point of D-train of X is Xj, constituted of three vectors OJ, OIDJ, WJ, which all these points are constructed as realization using a generator of the prior priority model PUWF, the priority distribution, and using the nonlinear dynamics computational model in order to compute OJ, OIJ, ID given WJ. So the first step is to construct a reduction using a principal component analysis of a big vector X in order to construct the training dataset related to X. So this is a classical formula in which underline X is a mean value of X estimated with a training dataset, and lambda and phi are the eigenvalues and the eigenvectors of the covariance matrix of X estimated always with the training dataset. The new random vector is H with a dimension nu, which is less than nx, the dimension of X, and H is centered and its covariance matrix is identity matrix. Since H is non-Gaussian, all the components of H are statistically dependent, even if the covariance matrix is an identity matrix. So in this case, it's a normalization. The training dataset, D-train, is then obtained classically by a projection of the training dataset D-train of X on the basis defined by the PCA. And so we have this training dataset D-train of eta for ND point, eta 1, eta d, ND vector, which are ND realization of H, and which are given by this formula. Now, because we have incomplete data for the target dataset and with a partial observability, the method which is proposed is to perform a projection of the NR target points. So the vector of target is psi R target with two components, two vector components, OR ID target, which is associated with identification observation, and the corresponding value of the control parameter WR target. So we perform a projection of the target set on the model, and so we have to solve this optimization problem consisting in minimizing the Euclidean norm of this expression, in which xi is related to the extraction of 5 times lambda 1/2, underline psi is the extraction of underline x. So with this projection, we obtain the projected target dataset, T target, constituted of NR points. Now, the problem is representation of the constraints, because in the proposed method, the constraints in Plum is taken into account using the Kullback divergence minimum principle. Maybe as you know, the Kullback divergence, if you want to introduce constraints in this principle, you have to describe the constraints in terms of mathematical expectation E of deterministic mapping, HC, nonlinear mapping of H equal a given vector. But since the target dataset is defined by a set of realization of the target, we have to transform this realization with this type of equation. But since NR is small, you cannot construct the statistical moments which are not converged. This is the reason why another approach has been recently developed in 23 using the Fourier transform of the probability measure. And with these mathematical results, we can express these constraints in terms of mathematical expectation in which HC is a nonlinear mapping which is explicitly given by this formula, and BC is explicitly given by this formula. Eta R target are the points of the target dataset are known. S is a parameter which is defined as that as a function of dimension mu. Now, we have to perform the probabilistic learning for hash under constraints using Kullback divergence. So first, we introduce the probability measure represented by density pH of H, which is estimated using the Gaussian kernel density estimation, in fact, a modification of this usual formula, and the training dataset for H with point eta j. And this is modification for any value of nu, that is to say for any dimension nu, we have exactly H is centered and covariance matrix is the identity matrix. So the learned probability measure for HUD, the updated value of H, as the plum under constraints, is represented by density PUD of HUD under this constraint, and this Kullback divergence minimum principle consisting in solving this functional optimization problem, finding the function P HUD, which is a PDF, find the P belonging to an admissible set as the integral over R nu of P eta, the logarithm of P eta over pH, which is a prior measure. And this admissible set is constituted of all the probability density function on R nu, this is a normalization condition, and the constraints here, which is the expression mathematical expectation of HC of U HD, this part, equal BC, this part. The Plum methodology for solving this problem consists in introducing classically Lagrange multiplier, in which lambda 0 is a scalar Lagrange multiplier related to the normalization condition here, and lambda is a vector valued Lagrange multiplier belonging to an admissible set related to this vectorial constraint. And so the PDF, which is solution of this optimization problem, PUHD, is constructed as a sequence of probability density function, pH lambda, of a sequence of random vector H lambda indexed by the Lagrange multiplier. And from the equation, you solve the equation using the Newton iterative method. But the question is, for given lambda in the admissible set, how could you construct the probability density function of H lambda? This performed under the constraints. This performed using the Plum under constraints that is developed for small training dataset, that is the hypothesis that is used, and allowing the learned probability measure to preserve the concentration of the measure in the region in which there is a random manifold. These are very important properties of the Plum. How is the Plum? Plum is based on the projection, so that introduced 16, of a diffusion map basis introduced by Kaufman in 2006, of a nonlinear stochastic differential equation, which is used as a MCMC algorithm generator, Markov chain Monte Carlo, ISD, stochastic differential equation, associated with a nonlinear stochastic dissipative Hamiltonian dynamical systems for which the invariant measure is a probability measure pH lambda, and the fact that a dissipative Hamiltonian system has been introduced, we can control the dissipative in the system in order to rapidly kill the transient part in order to get the stationary response. This figure shows an illustration of the capability of Plum to preserve the concentration of the learned probability measure in the neighborhood of a random manifold. In that case, the dimension of H is 9. The number of points in the training dataset is 400. The number of learned points is 400,000. The top figure, the top line, represents the simulation with a standard MC without Plum for component H1, H2, H3. The last line represents the same thing using Plum. These are clouds of points for component H1, for component H, I don't remember, I cannot read, it's H3, H7, H13. You can see that in the cylinder section, because we are in dimension 9, the support of the probability measure is very complex. And the training dataset is close-like to this graph, the clouds. You can see that without Plum, you have, with standard MCMC, you have a scattering of data, and so you lost the concentration of measure. You can examine the same properties in the probability density function. These obtained with the Plum. There are 5 modes in the probability density function of component H1, I think, and in that case, without Plum, you can see that. And this is the joint probability measure for H1, H2 here and here with Plum. So you can see that this the projection, the diffusion map basis of the Ito equation allows to discover the geometry of the support of the region in which the random manifold is localized, and to get and to keep, to preserve the concentration of the measure. Finally, for finalizing the elements of theory and before presenting the application, just a looking time. Where is it? Okay. So the surrogate statistical model can be constructed in different ways. In this case, the surrogate model, a statistical surrogate model, is defined by conditional statistics constructed with a big long data set generated by Plum and using non-parametric statistic approach for estimating any probability measure related to the observation and all the derivative of this probability distribution, such as statistical moments, confidence region, and so on. So you get this type of formula, for instance, for a component of the update observation. And you can see that this probability density function depends on W0. It's a conditional statistic for given W0 and depends on the realization constructed with Plum and the value of W0. Now, I will present some results of the nonlinear stochastic dynamics of the three-dimensional nozzle. The finite element model has 216 about 1,000 doves, is a big model, and there are 5,000 time sampling points for discretizing the stochastic dynamical equation. We consider 868 observation nodes that are all the nodes of the finite element of the nozzle exit section. And so the dimension of O is about 800,000. There are 8 identification observations, this is a dark point here, and the nozzle exit. And so the dimension of the identification observation is 8 times 500, the number of time sampling points, that is to say 40,000. And concerning the target dataset, there are only 40 points for performing the identification. So given this couple between OR target and WR target. So the training data set has been constructed with 400 points. There are two components for the control variables. The random vector x, for which the PCA is performed, is 880,000. And we can see that the value of nu, the dimension of h, is high because it's 307. This is the true stochastic dimension in this system, which is 307. And so we generate a learned data set with 50,000 points. The random control parameter is constituted with that controls the stochastic excitation is a parameter first which controls the level of statistical fluctuations, the amplitude, and the second parameter controls the frequency of the power spectral density function. That is to say, it is the frequency corresponding to the peak of the power spectral density function of the stationary stochastic process, which is underlying in the generating a stochastic excitation F. The uncontrolled random parameter U represents the Hooke random elasticity matrix C, which is in values in the set of all the positive definite metrics of dimension 6 times 6 using the Voigt notation, because the Hooke random is a fourth order elasticity tensor, which is transformed in a square matrix in Voigt notation. This stochastic model of C is such that the mean value, the expected mathematical expectation of C, is isotropic material, while the fluctuation, statistical fluctuation around the mean is anisotropic. So the anisotropic random C is written like that, in which G is a random matrix for which the probability distribution, random matrix with values in n plus, so it is not a vector space, is a cone in n plus, so it's not so easy. And this random matrix is constructed following the theory proposed in 2006 and depends on a hyperparameter delta that allows nivel statistical uncertainties in the Hooke random elasticity to be controlled. These figures give an illustration of the learned data set for H using Plum constrained by the target data set. This graph is the clouds for components H7, H13, H30. I recall that there are 307 components for H. And in these clouds, the blue points represent the training data set and the red points, the learning. So the learning points are shift because there are the targets. And this figure illustrates the same things for the probability density function of H7, and the dashed line corresponds to the training data set and the solid line to the learned data set. Now, I will present the final result concerning the validation for an observation that has not been used for updating the model, which is not used in the learning under constraint. So the value of W0, in order to limit the number of figures, the value, only one value of the control parameter has been selected, which is the mean value of the control parameter W. The results are presented, the vertical axis as a logarithm of the modulus of the Fourier transform, the Fourier transform of the random frequency of the time response of the dynamical system, and is expressed as in frequency of the frequency in hertz. So it is 0 hertz, 1,200 hertz. This figure compares the response of the linear system without nonlinear geometrical effects. This is a dark line, this line. And the blue line corresponds to the mean value obtained with a training dataset with nonlinear geometrical effects for nonlinear dynamical systems. So you can see that there is a significant effect of nonlinearities in the dynamical system. On the right figure, you can see again the blue line, which is the training, and the red line is the mean of the target dataset. So you can see that there is a difference that we have to decrease in the learning under constraint. These results obtained for the updating. So the blue line here represents always the training dataset. The red line here is the target dataset. The cyan line here is the mean value of obtained with the learn with Plum under constraints with the targets, and the cyan region is a confidence region corresponding to 95 probability level, and you can see that effectively the peak of the confidence region will coincide with the peak of the training dataset. So there is a good updating of the system, and you have the confidence region for the statistical surrogate model. As a conclusion, we can see that the Plum methodology under constraints that is proposed allows for addressing a problem which is not so easy for predicting updated statistical surrogate model, for a parameterized, uncertain computational model with stochastic excitation in a nonlinear, uncertain dynamical system. The major difficulties that have had to be taken into account is the high dimensionality of this problem, the partial observability. We have only a small number of identification observation for updating and a small number of points for target dataset. This is the case of incomplete data. And we have only a small training dataset for Android for a big system. The surrogate model properties that is proposed is purely probabilistic, is not represented by an algebraic model, but by a learned probability measure for which we have a generator, and they provide an efficient representation of output statistics using only conditional statistics derived from the learned dataset for the updated stochastic system. Thank you for your attention.
Thank you very much, Christian, for the very nice talk.